जाइंट मॉलिक्यूलर स्ट्रक्चर्स, जाइंट स्ट्रक्चर का हम वर्ड जब भी यूज करते हैं तो हम बात कर रहे थे नेटवर्क ऑफ ईदर कोवलेंट बॉन्ड्स जो कि हमारे पास मॉलिक्यूलर जाइंट स्ट्रक्चर में होते हैं या मेटालिक बॉन्ड्स में, कि उनमें भी जाइंट स्ट्रक्चर एग्जिस्ट करता है लेकिन बेसिस मेटालिक बॉन्ड्स की होती है, या आयनिक जाइंट स्ट्रक्चर, उनमें भी जाइंट स्ट्रक्चर होता है लेकिन बेसिक आयनिक बॉन्ड्स की, आयनिक लैटिस की होती है। नेटवर्क स्ट्रॉन्ग बॉन्ड्स का हार्ड टू ब्रेक होता है, मेल्टिंग बॉइलिंग पॉइंट्स ऑफ कोर्स इनके जनरली हाई होंगे। अगर कोवलेंटली बॉन्डेड स्ट्रक्चर्स की बात की जाए तो हमारे पास थ्री डायमेंशनल नेटवर्क्स आते हैं और वो कोवलेंट बॉन्ड्स के होते हैं, वो थ्रू आउट द होल स्ट्रक्चर एक्सटेंडेड होते हैं। हम इन स्ट्रक्चर्स को इसी वजह से जाइंट मॉलिक्यूलर स्ट्रक्चर्स या जाइंट कोवलेंट स्ट्रक्चर्स भी कहते हैं, ठीक है। और इन्हें फिर जो हमारे पास रिजल्टिंग मॉलिक्यूल्स होंगे इन्हें हम सिंपली जाइंट मॉलिक्यूल्स या जाइंट कोवलेंट मॉलिक्यूल्स इस तरह से बुलाएंगे। They have high melting and boiling points क्योंकि हमारे पास लार्ज नंबर ऑफ स्ट्रॉन्ग कोवलेंट बॉन्ड्स हैं जो लिंक कर रहे होते हैं पूरे स्ट्रक्चर को। एलिमेंट्स जैसा कि कार्बन है जो कि हमारे पास ग्रेफाइट और डायमंड की फॉर्म में होता है, या कंपाउंड्स जैसा कि सिलिकॉन डाइऑक्साइड है, ये जाइंट मॉलिक्यूलर स्ट्रक्चर्स होते हैं और ये तीनों हम आईजीसीएसई में स्टडी कर चुके होते हैं। डायमंड और ग्रेफाइट डिफरेंट फॉर्म्स हैं सेम एलिमेंट के, ठीक है। डिफरेंट क्रिस्टलाइन या मॉलिक्यूलर फॉर्म्स अगर सेम एलिमेंट की हो तो उन्हें हम एलोट्रोप्स भी कहते हैं। दिस इज द डेफिनेशन वी हैवंट स्टडीड बैक इन आईजीसीएसई। एक आधी रेफरेंस बुक सच एज कंप्लीट केमिस्ट्री में तो है मौजूद लेकिन एक्चुअली सारी बुक्स में नहीं होता, तो फिर इसलिए हमें नहीं पता होता। कोई एक ऐसा एलिमेंट जो डिफरेंट फॉर्म्स में, क्रिस्टलाइन फॉर्म्स में या मॉलिक्यूलर फॉर्म्स में एग्जिस्ट करता है उसे हम एलोट्रोप्स कहते हैं, ठीक है। एलोट्रोप्स डिफरेंट क्रिस्टलाइन फॉर्म्स हैं सेम एलिमेंट की। ये टर्म सिर्फ अप्लाई होती है सॉलिड्स को, डायमंड, ग्रेफाइट और बकमिस्टर फुलरेन या सिंपली फुलरेन जो है वो एलोट्रोप्स हैं कार्बन के। डायमंड ग्रेफाइट से आप फेमिलियर हैं आईजीसीएससी से। बकमिस्टर फुलरेन या फुलरेन का भी एक थोड़ा सा कॉन्सेप्ट आईजीसीएससी में ही ऑर्गेनिक के चैप्टर के पहले पहले पेज पर एग्जिस्ट करता है यूजुअली। वेल आप सारा कुछ यहाँ पे देख लेंगे और बड़ा अच्छा कंपैरिजन होगा एंड इट वुड बी मोर डिटेल्ड टू। सो लेट्स गेट स्टार्टेड विद ग्रेफाइट, ठीक है। In graphite, carbon atoms arranged होते हैं planar layers में. Planar layers means they exist in the plane. ठीक, we are talking about a two-dimensional structure, a structure that can be easily shown by a simple drawing on a paper like this one, right? So जब आप layers के अंदर बात कर रहे होते हैं तो कार्बन एटम्स अरेंज होते हैं हेक्सागॉन्स में, नीचे उसने वो हेक्सागॉन्स ड्रॉ भी किए हुए हैं। हर कार्बन एटम ज्वाइन करता है थ्री अदर कार्बन एटम्स को स्ट्रॉन्ग कोवलेंट बॉन्ड से। फॉर एग्जाम्पल अगर हम इस एक कार्बन एटम को कंसिडर कर लेते हैं तो हमारे पास 1, 2 और 3 स्ट्रॉन्ग कोवलेंट बॉन्ड्स एग्जिस्ट करते हैं। फोर्थ इलेक्ट्रॉन हर कार्बन एटम का ऑक्यूपाई करता है एक पी ऑर्बिटल, वो इसका पी ऑर्बिटल भी होगा, वो इसका भी होगा, वो इसका भी होगा, ठीक है। वो हर ऐसे कार्बन एटम का होगा, ठीक है। तो हमारे पास यूजुअली अगर किसी एक ही को हम देखें, एक हेक्सागन को देखें, तो आई एम गोना रेज ऑल ऑफ दिस, आई एम गोना कंसीडर अ पर्टिकुलर हेक्सागन। मैं ये आखिरी हेक्सागन इस केस में कंसीडर कर रहा हूँ। तो हमारे पास ये पी ऑर्बिटल्स हैं और एक इलेक्ट्रॉन सबका उसमें फ्री है। अब ये पी ऑर्बिटल्स हर कार्बन एटम के प्लेनर लेयर में ओवरलैप करते हैं साइडवेज। ये साइडवेज ओवरलैप करेंगे तो सारा ऊपर का पोर्शन ओवरलैप हो जाएगा, इसी तरह सारा नीचे का पोर्शन ओवरलैप हो जाएगा। सो एक्चुअली जो हमारे पास एक हेक्सागन एग्जिस्ट करता है, ठीक है, मैं इसके कॉर्नर्स थोड़े से हाईलाइट कर देता हूँ ड्रॉ करके, आपको अंदाजा हो जाएगा कि उसी हेक्सागन के ऊपर भी एक लेयर आपके पास आ जाती है, ठीक है, और उसी हेक्सागन के फिर नीचे भी एक लेयर आपके पास आ जाती है जो कि पाई का आपस में साइडवेज ओवरलैप होता है। द प्लेस और अ क्लाउड दैट वी कैन कॉल, जहां पर डीलोकलाइज इलेक्ट्रॉन, वो जो फोर्थ इलेक्ट्रॉन होता है उसका अबव और बिलो द कार्बन रिंग्स हमारे पास एक स्पेस बन जाता है where the probability of finding those electrons is the highest. ये इलेक्ट्रॉन क्लाउड ज्वाइन करते हैं अप टू फॉर्म एक्सटेंडेड ड्यूअली लोकलाइज्ड रिंग्स, क्योंकि हम सिर्फ एक हेक्सागन की बात नहीं करेंगे, इसके साथ ये भी एक क्लाउड होगा, इसके साथ ये भी एक क्लाउड होगा, इसके साथ ये भी एक क्लाउड होगा। सो फॉर अ ह्यूज स्ट्रक्चर, अ gigantic structure like this, it would join up all the extended delocalized rings of electrons. Layers of carbon atoms are kept next to each other by weak instantaneous IDID forces. अब उसकी वजह से होगा क्या, इस सारे स्ट्रक्चर पे फिर हमारे पास बहुत स्पेसिफिक प्रॉपर्टीज आती हैं ग्रेफाइट में देखने को, जो आपको एक नॉन मेटल के अंदर नहीं मिलती, ठीक है। नॉन मेटल्स यूजली बहुत हाई मेल्टिंग या बॉइलिंग पॉइंट्स नहीं रखते, लेकिन इस जाइगेंटिक स्ट्रक्चर और थ्रू आउट कोवलेंट बॉन्डिंग की वजह से जो लेयर्स ऑफ कार्बन एटम्स में होती है, एक बहुत ज्यादा एनर्जी की अमाउंट चाहिए होती है ताकि आप ओवरकम कर सकें. सो वी हैव हाई मेल्टिंग पॉइंट्स and we have high boiling points. This is not the only thing. Of course, it's going to have in high density. And next is softness. Graphite को easily scratch कर सकते हैं. Forces between the layers of carbon atoms, they're weak. Layers graphite की slide कर जाएंगी over each other. जब भी force apply होगी, layers readily flake off कर जाएंगी, यानी टुकड़े टुकड़े होकर इसके ऊपर से उतर जाएंगी. ये फ्लेकिनेस होती है जिसकी वजह से हम ग्रेफाइट को पेंसिल के तौर पे यूज करते हैं. जब आप एक पेंसिल को रब करते हैं अगेंस्ट द पेपर, तो वो एक लेयर पीछे अपने छोड़ती आती है, एक ट्रेल पूरी छोड़ती आती है. वी कॉल दैट ट्रेल हैंड राइटिंग. ठीक है. सो एक्चुअली वो ट्रेल क्या है? वो ट्रेल फ्लेक्स हैं या फ्लेकिनेस है उन लेयर्स की जो पेपर के साथ स्ट्राइक कर रहे हैं, और बिकॉज ऑफ वीक फोर्सेस वो इजीली पेपर के साथ ही स्टिक कर जाते हैं. पेंसिल स्लोली यूज होके छोटी होती रहती है हमारे पास, और हम कहते हैं कि वो पेंसिल लेड पेंसिल में है, वो स्लिपरी फील दे रहा है और वो हैंड राइटिंग प्रोड्यूस कर रहा है. इट्स अ प्रीटी गुड कंडक्टर ऑफ इलेक्ट्रिसिटी, सिंस बीच में जो वीक फोर्सेस हैं वो डॉटेड लाइन से शो की हुई हैं. यहाँ पर इलेक्ट्रॉन्स फ्री टू मूव होते हैं इन बिटवीन द लेयर्स. ठीक है. ये बहुत इंपॉर्टेंट बात है जो उसने यहाँ पर अलोंग द लेयर्स लिखा हुआ है. लेट्स एक्सप्लेन दैट विद द हेल्प ऑफ दिस डायग्राम. इसका क्या मतलब है? इसका ये मतलब है कि अगर आप इसकी लेयर्स के दरमियान में कोई वायर पुट करेंगे इस तरह से कि आपने इस तरह से करंट को पास करना हो, या आपने इस तरह से करंट को पास करना हो, तो करंट पास हो जाएगा. अगर आप इस तरह से करंट को पास करने की कोशिश करेंगे, या आप इस तरह से करंट को पास करने की कोशिश करेंगे परपेंडिकुलर टू द लेयर्स, तो करंट पास नहीं होगा. All right. So what we are trying to talk about here is that along the layers, electrons can easily move since the clouds exist in those forms. यहाँ पे भी cloud है, यहाँ पे भी cloud है. So the electron would be able to move from cloud to cloud. But if you're talking about this, there is an entire packing of layers through which the electrons are unable to move. So perpendicular, there won't be any electricity. So yeah, graphite is a fair conductor of electricity, but that's only along the layers, not perpendicular to the layers. Does that make sense?
Yes, sir.
Good, good. That has been used in a lot of MCQs, and you notice the same thing when you try to solve topicals. Moving on, diamond. In diamond, each carbon atom forms 4 covalent bonds with other carbon atoms, and we can easily show, since this diagram is a little difficult to draw. So what I'm going to do is that I'm going to consider this as carbon atom, and this one, this one, this one, and so on and so forth. So if we talk about carbon atoms, every carbon atom is bound to 4 other carbon atoms by 4 single covalent bonds, and that system goes ahead and extends to the entire giant structure. Carbon atoms are positioned around each other like a tetrahedral arrangement, since we have been calling this as a tetrahedral arrangement. So the network of carbon atom extends almost unbroken throughout the whole structure. The regular arrangement of these atoms give a diamond a crystalline structure, right? So the properties of diamond are related to its structure. We can safely say we can relate every property to the diagram we have above. So there are high melting and boiling points since there are strong covalent bonding throughout the structure. And let's compare diamond and graphite with one another. And I'm going to put some properties into comparison since that has been a part of past papers. So every carbon is bonded to 3 other carbon atoms, my bad. In this case, 4 other carbon atoms. In this case, 3 other carbon atoms, right? So of course, this one has more bonds, and I'm talking about the covalent bonds, right? This one has more covalent bonds. This one has slightly less for the same amount of structure. So of course, this one's gonna have higher melting and boiling points. Though both have higher melting and boiling points, but in comparison, this one would have higher, and this one would have lower melting and boiling points. When compared in density, of course, this one would have more tighter packing since it has 4 bonds per structure part, and this one would have lower density, right? So on and so forth. This one is rather soft and slippery. So this one would be hard and brittle. So you'd notice just because of these 4 covalent bonds in a tetrahedral structure, some of the properties, though they are same pretty much, but may show a change in comparison to one another. All right. So moving on, a lot of energy is needed to break these strong bonds and separate the atoms. Hardness, diamond cannot be scratched easily. It's difficult to break the three-dimensional network of strong covalent bonds. To be honest, diamond is the hardest natural substance on the planet. Natural. We have many artificial substances that are harder than diamonds and can easily scratch diamond. Moving on, it does not conduct electricity. All of the 4 outer electrons in every carbon atom are involved in covalent bonding. This means there are no free atoms available to carry the electric current. Most of the diamonds used around the world have been mined from the Earth's crust. However, artificial diamonds can be made by heating other forms of carbon under high pressure. Artificial diamonds are too small to be used for jewelry, but they can be used for drilling tips. But this is now more of an underrated sentence since we're producing too many artificial diamonds now, and now we are using them in jewelry as well. Since the smaller the size of the diamond, the easier it would be affordable for a person of not being too rich but still being able to afford diamond rings, which are now a thing in the market, right? So moving on, silicon 4 oxide. Now there are several forms of silicon 4 oxide. Silicon 4 oxide is found in the mineral quartz, which has a pretty similar structure to diamond. And apart from these quartz crystals, which reflect the regular arrangement of silicon and oxygen atoms, based upon the same arrangement, to every silicon, there are attached 4 oxygen atoms, and to every oxygen, there is a silicon atom attached, so on and so forth. It would keep moving in the same way. All right. The similar thing is drawn over here. So each silicon is bonded to 4 oxygen atoms. Each oxygen is bonded to 2 silicon atoms. The formula for silicon 4 oxide is SiO2. So per molecule or per part, if we decide there are 2 silicons bonded to 4 oxygens, right? Since oxygen is bonded to 4 silicon, even if you understand it like this, or you understand as per their properties or combining powers, you would get the similar formula, and simplifying, you would be able to get it like this. So if we understand this or simplify it to this form, it means the same thing. So whichever way you understand it, you would always be able to come up with the same formula, SiO2, right? So silicon dioxide has the property similar to that of diamond since the structure is also tetrahedral, right? So the properties are much similar. It is going to be hard. It would have high melting and boiling points. It won't be able to conduct electricity. And sand is largely silicon 4 oxide. So sand also caters the same example. Now remember, the most giant molecular structures do not conduct electricity. One exception is graphite. Most do not conduct heat, but diamond is a good conductor of heat, right? So we have already quoted 2 exceptions in this case. Remember that not all metals have high melting points. Specifically, group 1 metals and mercury have lower boiling points than some non-metals. So do not use high melting point as a characteristics of metals unless you're only referring to transition elements, which distinguishes metals from most of the structures that they is that they conduct electricity when solid. So yeah, that is the property you can come up with and write as a first property of metal. Since all the metals on the planet can conduct electricity, no matter They are in solid form or liquid form, or exist solid as solids or liquids at room temperature, which finishes up the first part for us. Moving on to the second part, but before I do you have any questions from the first part?
No, sir.
All right. Okay, so fullerenes, graphite and diamond are not the only yellow drops of carbon. In recent years, substances called fullerenes have been made. The structure of many fullerenes is based on the rings of carbon atoms as the structure of graphite, but many fullerenes exhibit properties unlike those of graphite. The individual particles in fullerene may have one of their dimensions in between this many nanometers, 0.1 to 100. 0.1 nanometer is 10 raised to the power minus 9 meters. Particles of this size are known as nanoparticles since we can then read them in nanometers. Another form of carbon, graphene, can be regarded as a single layer of graphite. Fullerenes are allotropes of carbon in the form of hollow spheres or tubes. They are similar in structure to graphite in that each carbon atom is bonded to three other carbon atoms. Don't forget the arrangement in graphite. They contain rings of carbon atoms arranged in hexagons. In addition, many contain rings of atoms arranged in pentagons. Now, if you remember this hexagons and pentagons line, Buckminsterfullerene is going to come easier to you in terms of its basic structure. Now, this is the structure I was talking about. The first fullerene discovered is known as Buckminsterfullerene, C60. C60 because one molecule contains 60 atoms of carbon. That's not the only one. We're going to come up with many more, but let's start with this one. Buckminsterfullerene is a simple molecular structure. The C60 molecule has the shape of a football or a soccer ball. The carbon atoms are arranged at the corners of 20 hexagons and 12 pentagons. Now it contains both. Take a look. This one is a pentagon. One, two, three, four, five. And every pentagon is then surrounded by one hexagon, two hexagon, three hexagon, four hexagon, and five hexagon. And then it is next connected to a pentagon again. So in this way, you can see that C60 would be 20 hexagons and 12 pentagons. The bonds where two hexagons joins are shorter than the bonds between the hexagons and the pentagons, right? So if you are talking about to go with a similar structure and you are putting six atoms of carbon in a hexagon, of course they would have shorter bonds than the pentagons because it would have five carbon atoms. I guess this is easily understandable. As in graphite, some of the electrons in C60 are delocalized, but to a lesser extent than in graphite. Since the discovery of this C60 Buckminsterfullerene, many other types have been discovered. Some are ball-shaped, such as C120 or C20, C70 or 72. Um, Not exactly C20 is ball-shaped, but you may call C72, C120, and C60 as ball-shaped, since C120 is multiples of C60. Now, as you can see the pentagons and hexagons, I hope you understand the structure. Let's talk about the properties according to this structure. Now, properties are significantly different from those of graphite and diamond, specifically those of graphite. Now, it has a very low sublimation point. Now, they are not talking about melting point or boiling point, they are talking about sublimation point. So you should automatically understand either it would exist as a solid or it would turn into a gas or vice versa, but it won't turn into a liquid. So it turns from directly solid to vapor state if heated at about 600 degrees centigrade. Graphite only turns from solid to vapor at about 3700 degrees centigrade. So this includes melting and boiling both for graphite. This is because there are weak intermolecular forces between each Buckminsterfullerene molecule and no continuous layered joint structure as in graphite, hence the big difference between 600 and 3700. It is relatively soft because it does not require much energy to overcome the weak intermolecular forces. The comparison has also been given above in terms of its sublimation points. Moving on, it's a poor conductor of electricity compared with graphite because the extent of carbon delocalization is much lower. There are very less number of electrons available to freely move. It is slightly soluble in solvents such as carbon disulfide or methylbenzene, which means we are talking about organic solvents. Since neither diamond nor graphite is soluble in common solvents, it's different. It is more reactive than diamond or graphite. Buckminsterfullerene reacts with hydrogen, fluorine, chlorine, bromine, and oxygen. This is due to the relatively high electron density in certain parts of the molecule, specifically pentagons. Make sense? Okay, I hope it does. Moving on to nanotubes. Nanotubes and graphene are not a part of the syllabus, but you may be asked questions about the structure and related properties of an unfamiliar substance from any given information, a diagram, or a structure. That's why we take it as an extended part. Now, a second type of fullerene is a class of molecules described as nanotubes. Nanotubes are fullerenes that are hexagonally arranged carbon atoms like a single layer of graphite bent to form of a cylinder. Now you take a layer of graphite and then you try to bend it over so much so that you should be able to make a cylinder like this for the whole thing, right? The first nanotubes were to be made were one layer of carbon atoms in thickness. More recently, nanotubes have been made with thicker walls with several tubes inside one another. So you can put one tube in another, and then another inside one, and then another inside one. So you can keep on putting tubes, which can make it thicker. Although the diameter of nanotube is very small, it can be made relatively pretty long. The length of nanotube cylinder can be a million times greater than its diameter. Diameter is supposed to be small, of course, you can understand that, but the length can be really big. It's a pretty good example of how a nanotube would be like. So, moving on, nanotubes have characteristic properties. They have high electrical conductivity along the long axis of the cylinder. This is because, like graphite, some of the electrons are delocalized and are able to move along the cylinder when a voltage is applied. Since you convert it into a cylinder, you bring those electrons nearer and you make the flow easier, which increases the electrical conductivity, hence high electrical conductivity. They have high tensile strength. When a force is applied along the long axis of the cylinder, they can be up to 100 times stronger than steel of the same thickness. So yeah, they have a very good strength. Now let's define the strength. Strength means when you're going to put some load or weight on them, would they be able to bear it? Strength is divided into two types in physics. Now I'm going to discuss a little bit of physics to make the point clear. When the entire load is acting on a single point, we call it shear strength or shear load. When the entire load is divided in form of a proper surface like a box or something, then the load is divided and it is not a point load, then it puts the weight along a certain area. Then the strength becomes tensile strength. The able to withstand that pressure or that burden becomes tensile strength. So yeah, of course the tube is going to break if you're going to put up a point load, but if you're going to put up something that has a specific area and is not pointy, it would be able to withstand 100 times stronger than the steel of same thickness. So I hope you understand what tensile strength means in this part. So they have high melting points, typically about 3500 degrees centigrade. This is because there is strong covalent bonding throughout the structure. Fullerenes have a large range of potential uses. Scientists can attach reactive groups to their surface and metal complexes can be formed. Complexes is something different. We'll discuss it later in A2. Small molecules or atoms can be trapped in the cages of Buckminster fullerene, and the most probable medical use would be delivering drugs to specific places of the body. Nanotubes are used in tiny electrical circuits. Now, if anybody is fond of Marvel movies, they have already done it in Marvel movies that nanotubes can deliver specific drugs to any part of the human body wherever it is required without even going through the regular method of delivering drugs through the stomach or maybe intravenously. Nanotubes are used in tiny electrical circuits such as wires and electrodes and paper thin batteries. We have been able to make these, but in order to get them to market, we need to work upon them more. And we are actually working upon them a lot since we are having better and better batteries in our cell phones and any incorporated electrical tech like that. They can be incorporated into clothing, sports equipment for added strength. They have also been used in the treatment of certain types of cancer, right? So moving on, graphene. Graphene is a single isolated layer of graphite, all those hexagons separated, right? So if we take a single layer out of it, out of graphite, it would be known as graphene. The hexagonally arranged sheet of carbon atoms is not completely rigid and it can be distorted. So graphene has some of the properties of graphite, but they are more exaggerated. For example, graphene is most chemically reactive form of carbon. Graphite wasn't much. Single sheets of graphene burn at very low temperatures and are much more reactive than graphite. So, of course, if they are very reactive, reacting them with oxygen, which includes burning at lower temperature, would be possible. So, graphene is extremely strong for its mass since it has all covalent bondings and we have already taken out the weaker part of the structure, so yeah, it may act strong for its mass. For a given amount of material, graphene conducts electricity and heat much better than graphite because we are talking about a single isolated layer, and of course, the properties would be exaggerated. Since after graphene, we understood that if we are able to take single layers out of huge, gigantic structures, maybe single layers have exaggerated properties like graphene does to graphite, we may be able to do it with single layers of maybe metal sheets or stuff like that. It has been said that 1 square meter hammock made of graphene could support a 4 kg cat, but weigh would only as much as cat's whisker, which is very light and again can support a lot of weight. Potential applications of graphene include use in tiny electrical circuits, tiny transistors, touchscreens, solar cells, and other storage devices. We already have them in energy storage, solar cells, and touchscreens. But that is not marketed yet since that costs a lot. So once we are able to cut the cost too, we'll be able to market it as well, which finishes the chapter for us.